Dear students, Assalamu alaikum. In this lecture video, we will discuss carbon 13 NMR or C13 NMR, and also we will discuss polarization transfer and a type of carbon NMR which is C-DEPT, that is distortionless enhancement by polarization transfer. So let us discuss one by one. So for carbon NMR, we usually based on carbon 13 isotope. So carbon 13 NMR is due to the carbon 13 isotope present in the overall carbon 12, which is only 1.11% as compared to carbon 12, which is 19 almost 98.99%. And the percentage of carbon is very less as compared to the proton, where we use proton NMR, which is 99% abundant. Magnetic moment of carbon 13 is only 0.702, which is 1 by 4 times less than the proton. So the spin quantum number of carbon 13, that is I, is equal to half or 1 by 2, and the gyromagnetic ratio is 10.705. It is also 1 by 4 times less than the proton. So according to this, it means our intensity of the carbon 13 will be very low. So the intensity of signal is reduced to 1 by 4th of the proton NMR. So carbon NMR, the intensity is very low as compared to the proton NMR because of these factors, that is gyromagnetic ratio and the percentage abundance of the carbon 13 isotope and dipole moment. So due to less abundance, peak of the carbon do not split, and we doesn't consider or we the carbon spin coupling or splitting will be very less or reduced and cannot be considered. So types of signal due to non-equivalent carbon atoms, and the chemical shift value ranges from 0 to 240 ppm as compared to proton, where we take 0 to 12 ppm, and the DMSO D6 peak will be at 40.45 ppm in carbon NMR. Now let us we consider some examples that how we get carbon NMR signals. It depends on different type of carbons or environment of the carbon. So here we are going to take an example of ethane, where both carbons have same environment. So these are equivalent carbon. So we will get only one single peak of the two carbon atoms. The intensity is two carbon atom and the peak is only single peak, which represents that both carbon atom are same or equivalent. If we consider this example, ethane, propane, and so in propane, the terminal carbons are same, which is represented with A, while the internal carbon is B, which has different environment as compared to these two protons. So we will get two proton signals of CH3 at the upfield, whereas CH2 at downfield for one carbon. Similarly, if we have an ethanol, we will get two signals, one for CH3 and one for CH2. So this is for CH3 for one carbon and CH2 for second carbon, as it is attached with the electronegative atom. So this atom, the signal will be shifted downfield. If you look at acetone, here we have three carbons, but these two carbons are same. So we will get one peak for these two carbon, whereas carbonyl carbon gives us downfield peak of one carbon. Here in this case, we have four different types of carbon. So all these four carbon will give us four peaks with the intensity of one carbon each. And here is our CH3 carbon, which is D, which is fourth carbon, and then we will get this peak of CH CH3, which also be at upward, and then CH2, and then CX, which is the carbon which is attached with halogen. It is more towards the downfield. So we will get CH3 peaks upfield, and then CH2 peaks, and then single carbon peaks, that is carbon. If we look at the benzene ring, so here we have two groups attached with the benzene ring. One is a hydroxyl group and then NH2 amino group. So in this case we will get six different peaks. So we have 1, 2, 3, 4, 5 and 6 carbons, and each carbon has different environment. They are not equivalent. So we will get different peaks. So here first we will get CH peak, and then these two CH, and then this CH, and then this one. So all these are aromatic CH, 1, 2, 3 and 4. This is 1, 2, 3 and 4. And then we will get the carbon with nitrogen, carbon attached with nitrogen at number 5, and carbon attached with oxygen at number 6. That is towards the downfield. Then we have another. So we will get, this is propylene. So we will get the peak of CH3 towards the upside, and then CH2 peak, and at the end we will get CH peak. Similarly, we have nitrile group. So in this case we have two peaks. One is for CH3 and other is for carbon, which is attached with the nitrogen. And here we have a benzene ring with methyl group and hydroxyl group. So in this case we have these two carbon with same environment and these two with same environment, and these are different. So we will get CH peaks for two carbon. So here we have two carbon peak for CH and then two carbon peak for CH, and then carbon attached with CH3 and then carbon attached with OH, and this carbon will be the first carbon which will be present upfield from all carbon. So aromatic carbon will be in the middle, whereas aliphatic carbon in the upfield direction, and then the carbon attached with electronegative atoms towards the downfield. So in this way we will get different peaks for carbon NMR, and this is for conventional method for carbon NMR, or classic method, which is also called as classic method. And now we are going to discuss distortionless enhancement by polarization transfer, which is also called as C-DEPT. In carbon NMR, the low intensity of the signal is a problem. Therefore, intensity of the signal depends on difference in population of the lower and high energy spin states, that is Boltzmann distribution, which in turn depends on gyromagnetic ratio. The NMR signals will be directly related to the power 3 of the gyromagnetic ratio. Therefore, carbon NMR intensity is 64 times less than the proton NMR, because gyromagnetic ratio of carbon is 1 by 4th of the gyromagnetic ratio of the proton. So natural abundance of the carbon 13 is 1.1% as compared to proton. Thus, considering all these factors, that is Boltzmann distribution, gyromagnetic ratio and percentage abundance of the carbon 13, we will get 6400 times less signals than the proton signals. So for carbon 13 NMR, signals can be enhanced by transfer of polarization, that is population difference, by coupled proton in CH system. So we can enhance the population, or Boltzmann distribution, or polarization transfer, or we can polarize the nuclei with protons. So proton coupled with carbon will enhance the signals. So in this way we will get enhanced signals. So here we are going to discuss polarization transfer. It is the process in which NMR signals of the nuclei with low gyromagnetic ratio and lower Boltzmann population is enhanced by transfer of the nuclear spin polarization from nuclei with high gyromagnetic ratio, that is proton, and higher Boltzmann population. So the protons have higher gyromagnetic ratio and higher Boltzmann population as compared to carbon. So by with transferring this population towards the carbon, we get higher signals. So the proton will couple with carbon. In this process, nuclei with high gyromagnetic ratio are irradiated, while nuclei of the low gyromagnetic ratio, such as carbon, is being observed. Therefore, it is called as double irradiation. So this polarization transfer is also called as double irradiation. If we look at the graph or the peaks, we have two peaks of A1 and A2 here. When the double irradiation occurs, these signal will be enhanced with A1 and A2. So these signals will be enhanced. One will be in the positive direction and other will be in the negative direction. Then after 180 phase shift, both signals we get upward direction or in the same direction. So let us consider the example of the coupling of AX system in which A represents carbon and X is representing proton. Now we will discuss or we will consider the polarization transfer in AX system. Similarly, we will get polarization transfer in AX2 or AX3 system, that is CH2 or CH3. So in this way, in C-DEPT we get the signals of CH3, CH2 and CH, not only single carbon, that is C will not give us signal because the polarization transfer does not occur without proton. So here we consider AX system where A is the carbon and X is the proton, and these are the nuclear spin levels. If we look at the energy levels, at lowest energy level, both are in the same spin which are along the external magnetic field, that is alpha spin states. So both are in alpha spin states, whereas at higher energy level both are at beta spin states, and which is fourth energy level, and in between these two energy levels both the cases may be observed, that is one is in alpha spin state whereas proton in beta spin state, and in third direction and in energy level 3 the proton carbon is in uh, beta spin state whereas proton in alpha spin state. So these two are the intermediate, or in which one is alpha spin and other is the beta spin state. During nuclear transition, what kind of nuclear transition can be occur, which is from alpha to beta spin state? If we look at carbon, so for carbon it will be either from 1 to 3 or from 2 to 4. So these two possible transition will occur in carbon, that is from 1 to 3 and 2 to 4, while in X, which are protons, it is from 1 to 2 or 3 to 4. So these two transitions for proton can be occur from 1 to 2 and to 3 to 4. So during irradiation, when radio frequency is applied, if the proton from X2, which is at third energy level, if it excites from alpha spin state to beta spin state, now the population at this energy level 3 will be decreased. By decreasing this, the excitation of this A2 will be enhanced, and the A will excite from energy level 1 to 3, that is from 1 to 3. So A will excite from energy level 1 to 3. So in this case the A2 will enhanced because of the excitation of this proton. So this proton causes decrease in spin states or population difference at this level 3. So for this reason carbon spin state will be shifted from alpha to beta spin state. And due to this, if the spin state at level 4 is enhanced, so all these are at beta spin states, and due to this reason the spins it will causes reverse in direction of the carbon from this fourth to 2. So in this case the decrease in excitation will occur in this level. So that's why one is the positive signal and other is the negative signal. And same in the case if the X1 is excited with RF pulse from energy level 1 to 2, so it will enhance the signal at beta spin state from at the second energy level. So due to this enhancement of the nuclei at this position, due to Boltzmann population, here it will be increased due to this excitation of this proton. The nuclei at this stage will be more, so it will cause the excitation of this carbon A1 from 2 to 4. So this will transfer from 2 to 4. So in this case the excitation of the carbon or A1 is enhanced by the excitation of this one. If this X1 excites, it causes excitation of the A1 and it will jump from 2 to 4. And again, if the population at energy 4 level is increased, the other side will be decreased and it will come backward direction. So in this case, if one signal is in positive direction, the other will be in negative direction, but in both cases the signal will be enhanced, one in positive and other will be in negative direction. And after this the 180-degree phase change will occur. So here is the explanation written for all that we discussed for polarization transfer. So in this case we get enhanced signal of the carbon due to protons. Now C-DEPT, so this is the this technique can be used for the enhancement of the carbon signal. So during C13-NMR, when 90-degree X pulse is applied, it bends carbon 13 magnetization vector, but the bending of M splits into different vectors depending on CH, CH2 and CH3 groups. We discussed that enhancement occurs, but when 90-degree X pulse is applied, the magnetization vector of the carbon will split during bending or during spin flipping. The magnetization vector will be split into different vectors depending on type of number of protons present in the vicinity of that carbon. So if we have one proton, 2 proton or 3 proton, so the bending will be different for magnetic vector. So number of vector splits depends on number of hydrogen atom attached to the carbon. That is two signals, two magnetic vector, it will split, magnetization vector will be split into two vectors if we have CH. It is same like n plus 1, that is n represents number of proton. If there is one proton, then n, that is 1 plus 1 is 2. Similarly, if we have 2 protons, then 2 plus 1 is 3. So 3, it will be split into 3, and 3 plus 1, that is n is for proton. So in this case we have n plus 1. So n plus 1 will give us 4. So it will split into 4 signals. So here we have represented that splitting of the magnetic vector, that during this spin flipping the magnetic vector will split into different angles depending on number of protons present attached with that carbon. So due to this difference in degree of rotation and time of relaxation, the carbon signal will split into different peaks. So that's why for CH3 we will get quartet, for CH3 that is again CH3 quartet. CH2 we will get triplet, and for CH we will get doublet, and for C we will get no signals. So here we have represented the C-DEPT of 2-butanol, in which we will get this CH3 signal here with quartet, and here this signal CH3 for quartet, and CH2 will give triplet, and this CH will give doublet. So this technique can be exploited to differentiate CH, CH2 and CH3 groups. Carbon which is not bonded to any hydrogen or proton cannot be detected by C-DEPT technique. So this is the another carbon technique which is used to differentiate between CH, CH2 and CH3 groups. So thanks for watching my video. In our next lecture, we will discuss nuclear or Hazer effect, and then we will move to the 2D NMR, and in 2D NMR nuclear over Hazer effect is also applicable, and we have different types of 2D NMR which we will discuss in our next lecture videos. Thanks for watching my video.